Hello everyone and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to have a little look at inodes. And we've talked about them before and we kind of glossed over a few details. And now we're going to go back and tell you a little bit more about these things that we just sort of ignored before. And we'll start with file modes. So there is a 16-bit file mode vector, bunch of bits, and you're probably familiar with some of these already. So you know about the octal bits that we use for permissions. We can do chmod 777 if we're feeling lazy, which gives everybody execute, write, and read permissions. And then we have those permissions for our group, followed by those permissions for the owner, a sticky bit, a set group ID, and a set user ID. So these are all things that we can have. Now, all of these can be combined, so we can use whatever combination we want. In addition to this information, the inode also stores something about the type of file. And these in bold here are mutually exclusive. So you only get to pick one. So if bit 12 is set, you have a FIFO. If bit 13 by itself is set, this is a character device. If bit 14 is also set, then it's a block device. So notice here on bit 14, if it's all alone, it's the only bit set, this becomes a directory. But if bit 13 is set, as we said already, this is a block device. If bit 15 is set by itself, then this is a regular file. If 13 over here is also set, it's a symbolic link. And if 14, its next door neighbor, is set, it is a socket. So that's the file mode. Other things in the inode, we have flags. And we have lots of them. We have 32 bits of them. So if we look at the low word for the flags, we see here at first we have a secure deletion flag, which says if you delete this file, shred it, wipe it, don't just say the space is available. We have a preserve for undelete, so it's kind of an opposite flag. We have a flag to say this file is compressed. We have a synchronous writes flag. In other words, don't cache when you're writing to this file. We have a flag to say a file is immutable and should not be changed. We also have a flag that says please only append to this file. Now I should point out that many of these flags are here, but their support is non-existent. Not all of these things are supported by the operating systems. There's a no dump flag or a flag to say please don't update the access time. Now, if you study Windows forensics, you will see that there is a similar flag for Windows directories. We have a dirty compressed file. We have a file with compressed clusters. And then we have a please don't compress this file flag. We have a flag that says this inode is encrypted. Another one for saying this directory has hash indices. We'll talk about what those mean in a future video. We can talk about AFS magic numbers. We can talk about data that has to be written through a journal. So you must use the journal when you write this data. We also can say this file, the tail of it cannot be merged. So you can't merge it together with something else. And that's only half of them. So what's in the other half? The other half contains things like this. The directory entry requires synchronous writes. So you can't cache the directory entry updates. This is the top of a directory structure. This is a huge file. This inode uses extents. We'll talk more about that in another video. It's fairly common. This inode stores large extended attributes. Typically, those extended attributes are ACLs, access control lists, but they can be other things as well. This is a deprecated flag that says there are blocks past the end of file marker in this file. There's an unused flag. There are a couple of flags related to snapshots. So here's one that says this is the snapshot. This one says the snapshot's being deleted. And this one says the snapshot shrink operation completed. There's also one for inline data. This can be useful when you have smaller files, and it can help speed up your I/O. There is also a reserved for ext4 library flag. Also in the inodes, we have timestamps. So in the lower 128 bytes, we have 4 timestamps: change, modify, access, and deleted. And these timestamps are stored in 32-bit values that are seconds since the epoch in 1970. Now, if we have an ext4 file system, typically on disk, the inodes are 256 bytes, and the current size of the actual inode is 156 bytes. So there's some room to grow, and there are extra timestamp values in the upper bytes. So what they do is the lowest 2 bits out of a 32-bit value are used to extend that timestamp to a 34-bit value. So currently the 32-bit values will overrun in about 2038. By extending it by 2 bits, it won't overrun past 2400 something. We'll all be dead by then, but who knows? Maybe our ancestors will still be running Linux and still doing forensics. The upper 30 bits are used to store the nanoseconds that should be added to the timestamp. So you now have nanosecond accuracy on these timestamps. So that's a little bit more detail on parts of the inode. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.